thank you very much, Robin, for the introduction, and thank you to all the organizers for setting up this wonderful workshop. The title of my talk is Thermalization via heat radiation of an individual object thinner than the thermal wavelength. With the title of that, you don't need an abstract. And it's actually work that was still done when I was here with my group at the Vienna University of Technology, and the real hero of all this is Christian Wuttke, the PhD student who did all the experiments and also most of the analysis, together with a bachelor student, Michaela, who did some of the thermalization measurements, and with theory support from Władysław Gulik and Matthias Krüger, and the resonators that you will see were fabricated in Jena in the group of Manfred Rothardt. So we are studying the heat radiation of nanofibers. These are silica fibers with a diameter smaller than the wavelength of optical or visible light. Why would one do this? Well, these fibers are dear to our heart because we do quantum optics experiments with them. So we couple atoms to the evanescent field surrounding such ultra-thin optical fibers, or we use such fibers to couple light into resonators. But it turns out that knowing how such a nanoscopic object thermalizes can also have applications, because we have more and more nano devices around. And for example, in optomechanics, you would also like to know how such a small mirror thermalizes if it's heated, because it reflects and partially absorbs some light. And well, the thermalization or heat radiation is also, for nanoscopic objects, is also relevant in environmental physics, where you would care about the absorption and emission, for example, of heat by soot particles, or even in interplanetary dust, so in astrophysics. And when you look at such experiments here, then typically the nanoparticles are not monodisperse. You have a variation, and in our case, it's one well-defined fiber. I will come to this. Now, talking about the thermal radiation to this audience feels a bit like carrying coal to Newcastle, but just very briefly, if we consider a black body that is in thermal equilibrium with a radiation field, then the power spectral density is given by Planck's law, and that depends on the density of states and the temperature-dependent occupation of these states. And if you then integrate this Planck's law, then you find Stefan Boltzmann law, so that the total radiated power scales with the fourth power of the temperature. Now, this is true for a perfectly black body, and if you then want to describe a real material, then you add some correction factor here, which is the spectral emissivity, which, for example, in the case of silica, our fibers are made from silica, is 0.8, so it's almost black. So you see that there's something weird here already, or in the definition actually, we consider this emissivity here as a surface property, but of course for silica to have such a large emissivity, which means, according to Kirchhoff's law, also large absorption, while silica is transparent, you actually need a infinitely large half space of silica. So if you look into an infinitely deep space of silica, it's almost black, okay? But as soon as we talk about objects that are not infinitely thick, and then we have to consider the effects of thermal radiation at small scales, then things are different, because shape starts to play a role. And in this case, we can see that, or it has been shown, that heat radiation can be partly polarized, can be partly coherent, is strongly enhanced in the near field, and in particular is a volumetric effect. So the radiation of heat does not only come from the surface, it's not a surface emitter, but it comes also from within the material, in particular if you have such a transparent material as silica. Okay. Now, there's a lot of work, as we will also, or have seen here and will see. So what can we contribute? Well, we actually have a material, a fiber with a predetermined shape. So we take a standard step index optical fiber, and in a heat and pull process we reduce its diameter, and we have a priori knowledge of the final diameter of, for example, 500 nanometers, and we reduce this, as I said, in a heat and pull process. Here you see a plot of the fiber radius as a function of position along the fiber. So typically the length of this taper transition here is a few centimeters. We work with fused silica, which is a well-known material, so we can, using literature values, find both the real part and the imaginary part as a function of wavelength of the refractive index. And here you see the imaginary part, which corresponds to absorption, is essentially 0 over a large spectral range, and in particular in the visible, where light does not absorb. And the diameter of our fibers, it turns out to be smaller than all absorption lengths of the thermal spectrum. So also where glass absorbs here in the infrared or for short wavelengths, still our fiber is much thinner than the absorption length. And what I will show you is that we devised a very precise method for measuring the temperature change of this fiber using some interferometric measurement, and that this allows us to measure the thermalization dynamics, and in particular with that the total radiated power. So it's not a relative measurement and a spectrum that we measure, but we really measure how much power the fiber radiates in total. Okay, so the tapered optical fiber schematically shown looks like this. We have a step index optical fiber with the fiber core and the surrounding cladding, and then we narrow down this fiber to a diameter, say, of 500 nanometers over a length of a couple of centimeters. And what is special about this tapered fiber is that we integrate into the unprocessed part of this fiber a fiber Bragg grating. So this is a mirror, and that means that we have a Fabry-Perot resonator, fiber-based Fabry-Perot resonator with such an ultra-thin section inside, and the light is reflected back and forth and goes through this thin fiber here. And the resonance frequency of this resonator is then, of course, highly sensitive to optical path length changes, in particular of this nanofiber, which may get hot. And then we measure, thus, the temperature changes by recording the optical path length change via the spectroscopy of our resonator, because the resonances shift. So the spectrum of this resonator is then just a typical Fabry-Perot-like resonator. So let's start with the lower spectrum, where you have resonances appearing every 1.5 gigahertz, and the finesse, so the ratio of the free spectral range and the width of our resonances is almost 100. And from this, actually, you see that the tapered transmission, so the intracavity losses include, of course, you have to squeeze the light through this thin section, and it has to arrive at the other side and go back and forth. This tapered transmission is actually quite high. It's almost only a few % loss in total. And now, if this is actually the spectrum, if you match the polarization of the light to the major axis of the fiber, which is slightly birefringent, okay? And if you tilt the polarization, then you see that you have non-degenerate polarization modes, which can turn out handy if you want to know in which direction the frequency shifts. You can make these two modes a bit different in height, and then you have a kind of also a direction in the spectrum. We will see this. And now the measurement principle is the following. Our resonance frequencies are given by the condition that the round trip length corresponds to an integer multiple of the optical wavelength, and that determines the resonance frequencies. And then we can we have our laser at a fixed frequency, say here where this blue line is, and we record the transmission of this laser, which we launch into the fiber. We record the transmission, and if we now change the temperature of the nanofiber here, its optical path length changes, and thus the resonances shift, and we will see a resonance passing by and a flash of light going through the fiber when the resonance scans over the frequency of the laser. And if we see two consecutive resonances passing by, then we know that the optical path length has changed by half the optical wavelength. So every time we see one resonance going by, half a wavelength has passed. So the optical setup that we use for this purpose is shown here. So we have our fiber inside a vacuum chamber, ultra-high vacuum chamber, so that it is not thermalized via gas transport of heat. And we send our spectroscopy laser, which is a diode laser, through the fiber, have a dichroic mirror, and record the transmission of this spectroscopy laser through the fiber. And we can heat this fiber by sending a heating laser through the fiber, which we can abruptly switch on and off, and which is separated from our probe laser here with this dichroic mirror, okay? And then the heating of this nanofiber section is caused by absorption of our heating laser, which is much stronger than this probe laser, because there are pollutants on the nanofiber surface, and they cause some very small but strong enough absorption so that we can heat the fiber with this heating laser. We can check that by varying the pressure of the chamber, that indeed gas transport does not play a role, so that the temperature changes are not depending on the pressure in the pressure range of this vacuum that we have here. And we record in real time the transmission signal with these photodiodes. And if we do so here is in the transmitted intensity as a function of time. And if we now switch on our heating laser, then you see resonances passing by, dang, 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 slower, 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 and then it's thermalized, and then we switch the heating laser off, and again, taka, 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 past come resonances, okay? And here we actually deliberately choose slightly tilted polarization so that you see that indeed the opposite sign of dynamics takes place on both sides, okay? Because these are two modes which are almost the same and which are only split by this little birefringence, and there is a large one and a small one which is on the left for the heating, and then the small one is on the right for the cooling. So you see that the resonances actually shift in one direction for heating and in the other direction for cooling, okay? And now we can simply take these timestamps of resonances passing by, and from that establish a dependence of the optical path length as a function of time. So this is what I show here. So optical path lengths change as a function of time. Okay, and you see when you heat, the optical path length increases and then stabilizes, and then when you switch off, again the optical path length goes back to its initial value, and you see that the dynamics here takes place on a time scale of a few hundred milliseconds. So this is the thermalization time scale. And now our task, in order to derive quantitative statements about the thermalization beyond what you see here, is to model this thermalization. And for this, we established a fully ab initio thermodynamic model of the fiber that takes into account the heating by the laser and the cooling by the heat radiation and the conduction of heat along the fiber and also gas transport. Here are these processes shown, so gas transport, conduction and radiation. And we make some assumptions for this model. So first of all, we make the assumption that the cross-section of this very thin fiber is actually thermalized, so that we don't have temperature gradients in the transverse direction of the fiber. We assume that the heating is due to surface absorption of the laser light that goes through the fiber and not volume absorption. But it turns out that our quantitative predictions of our model don't depend strongly on this. So we could also assume that it's volume absorption. And we assume that there is no heat flow through the tapers here, because we thermalize the fiber here at a given temperature, and the heat conductivity of silica is actually very low. It's a very good thermal insulator, so to speak. And then our path length change allows us, we can theoretically predict the optical path length change from the temperature profile that we get from our model. And here into this goes the thermo-optic coefficient. So the index of refraction of the glass changes when the fiber changes temperature, but also the thermal expansion of this fiber. So when it gets hot, it gets longer, and this also enters, okay? There are some uncertainties. The largest ones for this modeling are the fiber radius. So we make the fiber and know that a priori the radius is known to within 10 plus minus 10%, but there's no easy non-destructive way of measuring this a priori. We need good transmission. We can't put the fiber into an electron microscope before using it for the experiments, because that deteriorates the fiber. So we live with this uncertainty here. And the fused silica extinction coefficient has also some variation. And so what we do in order to take into account these uncertainties is that we solve our model for all combinations of the minimum and maximum radius and minimum and maximum extinction coefficients, and then take the extremal predictions as defining a band of predictions of our model, okay? And as I said, all this is completely ab initio. And for the thermal radiation, we can now take a very naive approach, which is just take the emissivity of silica and Stefan-Boltzmann law. Now, this is, of course, I already hinted on the fact that this must be somehow wrong, but we can also take, more correct description of the emission of the fiber. And there are two ways, maybe more, but two that I know that would give quantitatively correct predictions. One would be to take me theory and Kirchhoff's law in order to describe the absorption and emission by the cylinder. And the other one is fluctuational electrodynamics, which is the same idea as Planck. So we have some density of states, and we have here the material where we take the imaginary part of the dielectric constant, so which is the absorption and the thermal occupation. But the important part here is that we integrate these quantities over the full space. So we care about the material inside our structure. So it's really the shape of the structure is taken into account. And if you use this fluctuational electrodynamics calculation to compute the emissivity of the fiber, then it is shown here in blue. as a function of frequency of our heat radiation. Okay, so this is the fiber emissivity for a radius of 250 nanometers. And now, if you compare this to Planck's law, then you see that it is in a relatively narrow spectral range here, okay? And now we have, if we use this definition of emissivity, we would have to multiply Planck's law with this emissivity to find the power spectral density of the light emitted. And then you see that for low temperatures, Planck is to the left of where the fiber emits and absorbs, right? For high temperatures, Planck's spectrum is to the right. And for intermediate temperatures of room temperature, it overlaps. And that means that the radiated power of the fiber for temperatures which are around room temperature scale as Stefan Boltzmann law, so T to the 4. But if you are much hotter, then the spectrum moves away from the emissivity of the fiber, okay? And so the power does not increase like T to the 4, but rather like T to the squared or T to the power of 3, somewhere in between. So this is much less here. And if you compare this to the prediction of Planck's law of an emissivity of 0.8, essentially over all this frequency range for silica, you see that you expect a very different scaling. Okay, and now if we now use this prediction to make our model predictions, you see that it quantitatively corresponds to what we observe for the dynamics of the heating and cooling induced optical path length change. But our model now also allows us to attribute a temperature change. So here the right axis now is also temperature to this path length change. So far it was only we measure interferometrically path length. Now we have a model, so we know the temperature, and you see that here it goes to a couple of 100 degrees Kelvin. And now we can quantify this more than what we just show here. So here we see that we understand the dynamics of the path length or temperature change, but let us now quantify the equilibrium and the dynamics by looking at the maximum optical path length change upon heating and cooling, and let us quantify the dynamics by looking at the initial and final time constants of the thermalization. So these are the last two results. So first, equilibrium path length change, so that corresponds to equilibrium temperature that you reach. And you see that our data increases more or less, the temperature increases, or the path length increases more or less linearly with transmitted power through the fiber, whereas Planck's law predicts such a nonlinear scaling. And we see in particular that for large temperatures, there's a steeper increase of the equilibrium temperature than for Planck's law, because the fiber cannot get rid of its power, of its heat anymore, because its radiated power scales less strongly with temperature than for Planck. And we see the blue band is the fluctuational electrodynamics prediction, which quantitatively agrees with our observation. And then the time constants of thermalization, both for heating and cooling. So we can look at the initial time constant, which is shorter, and then the final asymptotic time constant for heating and cooling. So the blue dots and the red squares are the experimental data. The red bands and blue bands are fluctuational electrodynamics predictions. And you see again that the time constant here strongly differs from Planck by actually almost an order of magnitude. So this fiber thermalizes like 10 times less fast than predicted by Planck, because Planck highly overestimates the radiated power. So with this, let me summarize. I showed you that using our nanofiber-based Fabry-Perot resonator, we could monitor the optical path length change upon heating of a single nanoscopic object. we found an emissivity which is much smaller than for bulk silica. If you compare it, it's like a factor of 10 smaller than for a blackbody in this range of temperatures around room temperature. That depends, of course, as we saw. The radiated power for large temperatures scales much more slowly with temperature than predicted by Stefan Boltzmann law. And I presented an ab initio thermalization model for our tapered optical fiber and an analysis that yields excellent agreement with the observations. And then concerning the outlook, I should say that this was a short endeavor for us. Okay, we wanted to learn about the thermalization of these fibers and found fundamental physics, but we did not continue afterwards with further going studies. But of course, I would be very happy to have suggestions from you if you find that this system might be useful for doing further going measurements. Okay, and with this, I thank you for your attention, and I'm looking forward to your questions.